we demonstrate how to use Simulink multibody dynamics to make a beam rotate in the XY plane under the influence of gravity. We start from scratch and gradually build the program step by step. On the left, the initial state is shown. You can see the machine frame, the Revolute joint and the beam all connected to each other. On the right, the beam has already fallen significantly downward under the influence of gravity. Gravity acts downward, in the negative y direction. The icons on the left come from Simulink multibody dynamics. When we start building the program, we will drag these icons into the model. We will connect the fixed world frame to the machine frame. Then set the direction of gravity using the mechanism configuration block. Next, we link these two icons to the solver configuration block. We will also need the Revolute joint to allow the beam to rotate in the XY plane. The rotation axis of the Revolute joint is defined as the z-axis. If we were to give the Revolute joint a different orientation, the z-axis would rotate accordingly. In the figure, the z-axis is perpendicular to the screen, serving as the hinge's rotation axis. Note that it may seem as though the Revolute joint has dimensions. However, this is not the case, it is essentially just a pivot point. Therefore, the blue and gray arms of the Revolute joint have no length. Finally, we need a brick solid to model the beam. Let's start building the first part of the program in Multibody Dynamics.
In Multibody Dynamics, we drag various blocks into the workspace and connect them as needed. First, let's locate the world frame block. Next, we'll need the mechanism configuration block. The solver configuration block can be found in the utilities library. In the joints library, you'll find various types of joints, including the Revolute joint. Finally, the brick solid block is located in the variable mass library. The world frame is an XYZ coordinate system fixed to the machine frame. This coordinate system has a fixed orientation and cannot be rotated. The directions of the axes are shown in this figure. There are no configurable settings in the world frame block. We want the beam to rotate in the XY plane under the influence of gravity. In the world frame coordinate system, this appears to be the horizontal plane. However, that is not necessarily the case. If gravity points in the direction of the negative y-axis, then the XY plane is actually a vertical plane, and the beam will rotate downward within it. If you open the mechanism configuration block, you will see that gravity is set by default to point in the negative z direction. However, we want gravity to point in the negative y direction, and you can achieve this as follows. You can simply close the window. All settings are saved automatically because auto-apply is checked in the top right corner. Note that changing the direction of gravity does not alter the orientation of the world frame coordinate system. We can get a clearer view by looking down along the z-axis, that is, by viewing the coordinate system from a top view. In this view, the coordinate system appears as shown here, where the XY plane represents the vertical plane, and the y-axis points upward. This in the figure is perpendicular to the screen and points out of the screen. As always in multibody dynamics, all coordinate systems are right-handed. The solver configuration block has various settings, but we will leave them as they are. The Revolute joint block also has several settings, but again, we will not change anything. With the default settings, a frictionless hinge is modeled. We can imagine the hinge as a pin rotating frictionlessly within a sleeve. The rotation axis of the hinge runs in this direction and is perpendicular to the screen. We need to configure some settings in the brick solid block. Click on the brick solid, and you will see a beam in the shape of a cube and a local reference coordinate system at the bottom of the screen, which relates to the beam. By clicking on Top View in the top menu bar, we can see how the solid brick appears in the XY plane. The longest dimension of the beam is aligned with the x-axis, and we need to set the beam's dimension in the x direction to 100 centimeters. The dimension in the y direction is 10 centimeters, and in the z direction, it is 5 centimeters. The beam now appears as follows. The z-axis is perpendicular to the screen, and if the hinge is later attached to the left end of the beam, it will have the ability to rotate about it. Thus, the beam can rotate within the XY plane. Next, we need to set the mass of the aluminum beam by entering the density. The mass and mass moments of inertia are automatically calculated. Finally, we will give the beam a green color. Don't forget to regularly click on refresh. Our beam is now fixed. Later, we will attach the beam to the hinge, and for this, we will need to define coordinate systems at the ends of the beam. We will show how this works shortly.
Let's take a moment to revisit the whiteboard. On the left, we see the beam in its initial horizontal position, while on the right, it's rotated downward into a new position. Let's start with the left figure, where we've broken down how the machine frame, Revolute joint, and brick solid are connected using frames. To make this happen, we've drawn all three components separately and added a frame to each interface. The world frame is fixed to the machine frame, giving it a constant, unchanging orientation. On the left side of the Revolute joint, we have the base frame, which aligns perfectly with the world frame. On the right side of the joint, there's the follower frame, which matches up with the frame at the left end of the brick solid. Since the beam is horizontal, all the frames are beautifully aligned. This alignment works because we've ensured the z-axis of the world frame, the hinge and the beam are perpendicular to the screen. Now, let's shift our focus to the right figure. Here, the beam has rotated downward. Notice how the follower frame of the Revolute joint has rotated relative to the base frame. Its XY orientation has changed, while the z-axis stays fixed. Since the follower frame is attached to the frame at the left end of the beam, this frame rotates right along with it. Next, we'll jump into multibody dynamics to show you step-by-step how to place and define these frames. Let's get started.
Let's define the frames to ensure everything can be properly connected. The machine frame is already linked to the world frame, so we're off to a good start. Now, starting with the hinge, our first step is to define the base frame. The z-axis of the base frame is already determined. It's perpendicular to the screen. Since the base frame is firmly attached to the world frame, the two are essentially the same. Next, it's time to set up the follower frame. The z-axis for this frame is also predetermined. Keep in mind that the hinge involves two z-axes, one for the base frame and one for the follower frame, which perfectly align. If the hinge consists of a pin rotating within a sleeve, one axis is connected to the pin, and the other axis to the sleeve. When we click on the Revolute joint, we notice that there's no option to directly configure the follower frame. But don't worry. As we'll soon see, the follower frame is identical to the frame of the beam. This beam frame can be configured, giving us the control we need. Now we're at the beam. When you click on it, you'll notice a drop-down menu labeled Frames at the bottom of the screen, with a plus sign next to it. If you open the menu, you'll see there's already a port R coordinate system in place. Its origin is aligned with the center of gravity of the beam. But since we don't need this system, we'll go ahead and disable it. Next, click the refresh button and then hit the plus sign to start fresh. Follow the steps to create a new frame at the left end of the beam. To double-check that everything is set up correctly, click the frames icon. Once that's done, simply connect the follower frame to the beam's frame, and you're good to go. The program is ready to go. When you run it, you'll be able to watch the beam in action in the Mechanics Explorer. If the Explorer doesn't pop up automatically, don't worry. Just hover your cursor over the Matlab icon, and you'll see the Mechanics Explorer window on the left. Alternatively, hit F5 to open it. Pro tip, always hit Update first to ensure everything runs smoothly. You can use your mouse wheel to zoom in and out, or use pen view to move the beam into the perfect position. Since the beam's motion happens in the XY plane, it's best to switch to top view. Then, run the program again directly from the Mechanics Explorer. If the motion feels too fast or slow, adjust the speed using the slider bar. On the left side of the screen, you'll find collapsible menus filled with useful details about components like the world frame, brick solid, and Revolute joint. These menus show all the frames applied to each element. When you start the motion, you'll notice that the world frame doesn't rotate. It's locked in place. If you check the Connections panel at the bottom, you'll see that the world frame is connected to the base frame of the hinge. Now, open the Revolute joint menu. It shows that the base frame is fixed, and just as expected, the follower frame rotates along with the hinge. To make things even clearer, use toggle visibility of frames to view either a single frame or all the frames at once. Finally, open the beam's frame settings, and here's the confirmation. The frame on the beam is identical to the follower frame. It's rigidly attached to the beam and rotates with it as it falls, just like you thought. And here's a bonus, you're not limited to the top view. Switch to isometric view to explore the beam from different perspectives. You can even rotate it to see the motion from any angle you like. Thanks for tuning in, and have fun exploring your simulation.